Hi, this is Professor Cummings, and in this presentation I want to go over two concepts. One is Industry 4.0 and what that actually means. The next is the skills gap and what that means in terms of you and what opportunities that might be able to gather from that. Now you see here on the left we have John Henry, the steel driving man captured in legend and in song. And on the right we have Baxter, an industrial robot. Now, John Henry, the story behind him, if you don't know, he worked for the railroad. Someone introduced the idea of a steam drill to replace a lot of the workers. John Henry challenged it, competed against the steam drill, managed to beat it, but died of a heart attack. And later, the steam drill became the state of the art technology for the railroad industry, as well as mining and several other types of industries, simply because it had automation. Over on the right, Baxter, it's the really sophisticated 21st century robot that you'll start seeing in factories more and more. Now, what's some of the benefits of automation, going from automation, in other words, getting rid of somebody like John Henry and going to somebody like Baxter? Well, you're able to get more productivity when you go into automation. You're able to improve quality because you're able to remove variability. You're able to reduce labor costs. Baxter actually costs less than a year's salary, maybe less than half of a year's salary for a lot of people. It's able to improve safety because actually Baxter can get hurt or get damaged without actually hurting a person. You can put it in more dangerous situations. So you've got some really good arguments for going into uh, a state where you've got more automation. So on the left, you have John Henry, where it's very labor intensive. And on the right, you've got something called Industry 4.0. Now, what is Industry 4.0? It's the whole idea of going into a more automated, more computer-based industry where you remove a lot of the human factor, able to get a much more efficient, much more safe, much more productive manufacturing process, as well as having a lot more transparency, a lot better communication between different entities, and being able to respond better, a lot more flexibility. Now, that sounds like almost a utopia. You can have a factory without anybody working in it, without any human interaction. You're actually able to produce parts faster without having to worry about vacation time and all sorts of other issues. But really, what's the difference? What's stopping us from doing this tomorrow? Well, there's a lot of things, a lot of benefits to John Henry. Okay, a lot of benefits to actually having people in the in the marketplace, particularly in an industry. Some of them that are so simple that we tend to take for granted. Number one, John Henry can think. John Henry doesn't need to be programmed. You don't need to put an algorithm in place for John Henry to know what to do first, second, or third. John Henry can solve a problem, and more importantly, John Henry can make judgments. So when John Henry drops a wrench in the path of a machine, he knows to stop the machine and pick it up. He doesn't have to have that program into him. And anybody who's ever worked around machines has seen things like machines crash, machines, slam into something. Maybe it was programmed poorly, maybe something just happened to get in the way, but it could respond to contingencies or couldn't respond to contingencies the same way a person could. Along with that, you know, machines tend to need maintenance. They wear out. They tend to have certain parts that wear out. O-rings need to wear out. Cords get frayed. So different things have to be changed, and oil change get updated. Another one is communications. John Henry can actually communicate on his own. A actual person in a workplace can actually say what's changing, what's going on around them, can talk to a manager, can talk to the maintenance guy, can relay a problem, can say when a problem started and stopped. Baxter, all these things have to be programmed in. Something has to be put into place in order to make Baxter and Industry 4.0 actually work. So Industry 4.0, even though the whole idea is for it to be automated, it still requires a lot of human interaction in order to make it work. Maybe not in the downstream road, maybe not in the downstream, but definitely in the upstream. Somebody has to do all this programming. Somebody has to do the programming, somebody has to do this maintenance, and somebody has to set up this communication to make sure that Industry 4.0 actually works. So this brings us to the data security. Along with all of this new information being passed around, trade secrets can be made available, and there you have another issue with Industry 4.0. So we have data security that is also part of the question. So with all this, we come to a new issue that's been introduced in this dream of going from a more labor intensive industry to a industry 4.0, computer based automation, you know, lights out operations, and that is something known as the skills gap. Now, I'm not going to say the skills gap is purely based on reaching Industry 4.0. There's a lot of reasons and a lot of things that go into making up the skills gap. But the skills gap is definitely part of the issue with why we can't just switch to this tomorrow. There's a lot of different skills that are required to get us from where we're at now or where we have been in the past to this vision in the future of Industry 4.0. So what is the skills gap? What more goes into the skills gap to try and understand it? Well, the Department of Labor started looking at, or continues to look at, the blue line, which is how many people are out to be hired for a job, here in the blue. And here this dotted brown line is how many job openings actually exist. So that's the hires, and that's job openings, that's the hires. Now, as you can see, all the way going back to '06 through the recession and through the recovery, there was always more people than there were for job openings. But as things changed, as jobs started getting sent overseas or started being phased out, you can see that the gap between people that we had available to hire for a job and the jobs that were available started getting smaller and smaller until somewhere in 2014, 2015, we actually started overlapping. And then finally, we're at the point where we actually have more jobs than we have people that can actually fit them. Maybe there are people physically there, people physically who can come into these jobs, but they just don't have the skills that it takes to run those kind of jobs. Now, how big is this gap? How significant is this problem? We have had 500,000, that's almost half a million, or more than half a million jobs that went unfilled. They went unfilled simply because the skills weren't there to fill them. So what kind of skills did we have missing? A lot of the skills that were missing were things like people with a lot of STEM-based skills. One was design, regular engineering, mechanical engineering, electrical engineering works are designed for design of machines, design for design of manufacturing processes. You had people who this one skill was programming, in various types of programming. Other one would be maintenance, understanding plant layout, how a plant needs to be set up so that it's most efficient. And then, of course, believe it or not, skilled trades. Even in this day and age of automation, there will always be a place, and there still is a place for people who have a skill in their trade. So skilled plumbers, skilled pipe fitters, skilled millwrights, as well as skilled machinists. And keep in mind that manufacturing, whether we get the perfect Industry 4.0 or not, manufacturing is always moving towards automation. We're always trying to get the benefits of automation, more efficient, lower labor costs, and definitely a safer environment for people. But in order to do that, in order to get to that, we still need skilled people to implement this whole concept of a more automated, more flexible, more transparent workplace. So when we look at automation, we could break it up into various levels. Starting at the most local level as the device level. The device level is sensors, actuators, different types of hardware elements that you're going to interface with. The ability to shut a door and open a door quickly, the ability to shut a valve off and open a valve, remotely. Those are all things that would be on the device level, and those you could think as a very localized activity. Now, as you go down through the list of levels of automation, they go from a very local idea just down to a device, down to a machine where you're actually automating the machine itself, to automating an entire cell, which is various machines and various devices working together, to actually the plant level where you're looking at different cells interacting together and other devices, all the way to the enterprise level. So they go from more local down to the most expansive level. And that would be the enterprise levels where you have different factories, different plants, different vendors and manufacturers communicating and working together. Now, what would be an example of the device level automation? Well, I pulled up this little schematic and it just demonstrates a natural gas. So going from this point, this phase, all the way to the left of where you're actually retrieving the natural gas and storing the natural gas and sending it to a processing plant, to actually sending it to its end users. So different, power plants, different customers, commercial use, residential use, as well as natural gas powered vehicles. So what you're looking at here is just the network of how natural gas interacts. Now, this could be natural gas, this could be oil, this could be, looking at different things inside of a factory itself. What I want you to focus in on are these little red devices here and here, all throughout the drawing, all throughout the schematic. And consider these are what are known as actuator valves. What are actuator valves? Well, that's the device we're talking about. The actuator valve is simply a big switch that you can turn on using automation, turn on and off to shut a line down. Now, this could be for safety, this could be for lack of payment, there could be any number of reasons that you might want to shut down one valve over another, misdirect or redirect the flow of gas from one place or the other. And the way this is done is you have this actuator valve, actually being put onto a pipe or within the line, in the system. And through some sort of control mechanism, the valve is shut on and off. So if there's an issue, a safety issue, or some sort of need for an efficient and very quick turn off, you can do this remotely. So do it from some central location where you can shut the valve on and off. Now, how does this happen? Well, the technical term would be through a PLC. And this is a system that has to actually be programmed, and it's one of the most basic levels of programming and basic levels of automation that you'll see in any type of manufacturing or industrial situation. And that's the device level. So in order to understand PLC, you also have to understand something called ladder logic, which is essentially just a schematic for understanding this sort of control system. If you understand ladder logic, you can later go on and translate that into this type of device level control. Now, when you consider something like the machine level is a little more sophisticated than the device level. Now, to understand the significance of machine level, you can look at any phase of manufacturing, but we're going to look at machining. And you have traditionally conventional machines. So this is just a conventional lathe, and over here on the right, and a conventional knee mill. No computers to help program it, no automation, just a computer, or excuse me, a motor that actually turns a spindle, that holds the workpiece or holds a tool, and actually performs metal removal processes inside of the machine itself. This is a very skill-intensive operation that would actually require you to have either a journeyman or a very well-trained apprentice running this operation. Now, if we were to put some automation into this process, we could end up with something like this, a CNC machine with 5 axes. 5 axes meaning you can get much more sophisticated parts. So now you're getting a lot of very sophisticated curves, generating a lot of really unique geometries. You're able to produce the part with a lot more repeatability, a lot more accuracy. Now, how would you do this, or one of the skills that would be required? Well, with conventional machining, you actually need a very well-trained, skilled trade machinist. With CNC machining, what you need is a programmer. A programmer and somebody who has some very basic machining skills, who understands how the machine actually is supposed to work, but your primary skill set comes in the programming now. So you've moved the skill upstream. And what you see here is just the CAM software, computer automated or computer assisted manufacturing software, where you can actually generate your tool paths and get much more sophisticated cutting paths that you would with this machine, with that machine, than you would with a conventional machine. Other programming that could take place is straight G code, G and M code, which is just a different way of typing in the programming that goes into the machine tool. The computer-aided manufacturing can actually generate G and M code. And if you really want to go upstream, you could actually program the software that makes this. So then that comes in various different methods. In this case, I'm just showing you C++. So this is the machine level. And you can see a little bit more of this in the video coming up. So what you have here is the computer-aided design and computer-aided manufacturing portion. This is much more user-friendly than the actual setup of this machine if we were to use conventional milling. So a lot more automated, but you have it all the way down to the type of machine, to the type of cutting tool, as well as how the workpiece is held. Now that program can be sent to the actual CNC machine, and you can see it's very similar layout, very similar tooling, very similar work holding, and it gives the tool or the machine the actual access to all the complicated radiuses and geometries to make this component. This is significantly faster, significantly more efficient than the traditional method of machining. And what you can see is you end up with a very good part, a very well machined part at the end. Now, after the machine level, if we consider just the machine level, just working on the machine, the next level of automation will be the cell level. Now, what is a machining cell, or on any kind of a cell for that matter? But in this case, we're going with the machining theme. A machining cell is just various machines, various devices working in concert together. So you've got a machine, possibly a robot, possibly different types of conveyors, different types of safety, maybe that safety equipment. All these things are working together in order to produce either one or two families of components. And that makes up a machining cell. So as you can see in this example of a machining cell, you've got a robot, and it looks like you've got some sort of part that's being picked, running on a conveyor. So you've got an input, and you've got some sort of an output. I could have those backwards, but one's typically going in, one's typically going out. You've got a base of parts that the robot is working with, and it's doing essentially the same thing that a manual operator would do. I've seen these with CNC machines where the robot actually was loading parts into the CNC machine. The machine would start up automatically once the part's in place, shut its own doors, and once the machining operation has been taking place, the robot takes the part right back out again and puts it on the conveyor, and it goes out to its next operation. So a complete operation that goes on its own, just through the machining or through the cell. And this is what a machining cell does. So it's pretty complicated, but it's got all the different devices that we talked of in the past, and probably quite a few more. It's also got a lot of sensors. Like I said, one of the issues with automation is that they can't think. They can't have judgment. So what you need is different ways to give them that judgment. So here we have our good buddy Baxter, but we also have proximity switches. Baxter can't really make a judgment on what is good and poor quality. We could probably make it so that Baxter can detect something, but even then, he's still dependent on some sort of a sensor within himself. But you can also have this sensor or cameras to make sure that the part is actually within place. So that's another, form of automation that needs to be used, another area that needs to be programmed. So these are all things that have to be programmed, not just individually, like when we looked at the device level or even at the machine level. But now you got to get this machine and this all these corresponding devices, all these peripheral pieces of equipment to actually work with each other and work in a way that's synchronized, so that you can not only produce a good part, but you can continue producing good parts. And if you have any method, such as the camera or some way to judge whether or not something has gone wrong in the process, tooling is wearing down, something was misaligned, something wasn't in position properly, so that you don't end up having a crash. And I've seen that happen quite a bit with machining cells where something was sitting on the conveyor improperly and the robot started stacking the parts on top of each other accidentally. So you need some sort of way of clearing out that sort of judgment that a person could do that an automated cell is going to need help with. And that's another level of programming that's going to be required. So in this case, you would actually need some sort of manufacturing engineer. That's some skills that would be needed. You'd need the same electrical engineer or someone who could do some sort of programming, so PLC programming. The robot may have its own programming system. And then there's going to be some sort of way of monitoring this whole system, sending information into and out of the cell so the cell can be reset up and readjusted for other operations. So that's the cell level. So the next level after the cell level is actually the plant level. And this is where Industry 4.0 really starts to shine. Everything else that we've looked at, you've got some variation of that today that works, pretty successfully. Now, what we're moving to now is getting it so that all these different cells can work with each other. So you've got, robots that work with each other, HMI, human machine interfaces, again, getting all the sensors on the same page. Again, this is machine tool monitoring. So knowing what the machine is doing and when, and being able to understand this remotely. This is another major part of technology that is being programmed over the last 5 years or 10 years. I think it's been more like 5 years that we've been seeing more and more machine monitoring technology. So different types of apps, being able to monitor this on your phone and being able to respond back. These are part of the vision of Industry 4.0. So we've got Industry 4.0, we've got some sort of controlling system, whether it's an app from your phone, whether it's different controllers within the plant itself, or even outside of the plant, where you have multiple cells acting in concert with one another. So what you do when you get a situation like this, you get the benefits of this Industry 4.0. You've got flexibility, you've got something that's very responsive. You can actually get information from several places and make a judgment on what you need to change in the cell remotely. You've got interoperability. So these are the visions of Industry 4.0, to where you can actually have a lot more automation controlling the entire plant with a lot less human intervention. And I'm talking downstream. Now, as you can see, when you look at this from an upstream standpoint, this is where all your opportunity lies. So this is where all the programming takes place. This is where all the planning takes place. This is where all the engineering work takes place in order to achieve this goal. So these are the opportunities that are needing to be implemented. And again, this is part and a major part of the skills gap. These are the skills that need to be replaced. So if you were John Henry, this is where you're starting to look at to understand where your new place is in history. So we're talking about web-based programming, use of the cloud, and being able to utilize big data. Then, of course, the last level is the enterprise level. And all this is looking at different entities interacting with each other. So this could be different plants. This could be a plant and a supplier. This could be, two different divisions of the same company. So anytime you'd have something that deals with companies that might have to share communication with each other and knowing where things are in the value stream. So you're able to address the supply chain. So any type of supply chain issues can start to be addressed. You can adjust to customer demands. So if you have a customer up here, say customer entity A and entity B, and entity A needs to buy several more units of whatever entity B is producing, you can actually make some sort of adjustment. You have a lot more transparency. You're able to say, okay, what is going on between these different companies? Depending on how you want your data to be shared. And you can also share things such as best practices. So if you've got two companies, say this is a division in one part of the country and this is a division in another, or maybe these are two different companies, the enterprise level of automation allows that information to be shared automatically. So you can see how did one company or one division solve a particular problem, and what caused the problem and how the problem was diagnosed. So just kind of to summarize and review what the opportunities were for Industry 4.0 as well as the skills gap. So we got our good buddy John Henry. So there's a lot of opportunities out there. So understanding controls, PLC, controls as well as other types of controls for devices as well as machine tool, as well as machine design. Somebody has to come up with some way of designing these new machines and dealing with different demands that the industry is going to make. Also, another big one is software development, and then research and development and different types of innovation. And then, developing manufacturing processes that deal with a lot of these new technologies and be able to utilize them the most efficiently. Being able to program the machine, being able to, deal with the different types of software, different types of computer-aided manufacturing, as well as computer-aided design, which is constantly being updated. And then last and not least, data security. This is going to be one of the bigger issues when it comes to automation, as well as all this transparency. So there's certain information that you don't want to share, certain information that you do want to share, and being able to secure this, whether it's for a competitive advantage, whether it's trade secrets, or whatever it is. So these are the opportunities that exist in Industry 4.0. So if you want to go from the traditional type of manufacturing environment, very labor intensive, very manual, and go into see what's going to deal with or what you're going to deal with, then you go to Industry 4.0. These are the areas where you want to start to look. Again, this is Professor Cummings, and I'd like to thank you for watching this video, a particularly longer video than I usually do. Thanks for watching.